So let's go over the quiz, the extra credit on the quiz question. And it was this. Let f of x, this is not good, let me try it. Does this one work? That one should be good. Anybody remember what it was? Let f of x equal tan of arcsin
And some stuff.
and
It's
then
like
it was,
the square root of.
no, it was just 1 minus x
No.
squared.
Oh.
Okay? And I said we want to find the domain of f, and the range of f. Okay? Now, there are a couple different ways you could do this. One way is much easier than the other. At least to me, it's much easier. And I would suggest that in general, the way that I'm going to suggest to do it is the better way of doing these in general, regardless of what this is. As you notice, we have a composition of functions. We could think about this as some function, g of x, right? Where g of x is equal to 1 minus x squared. And then we take that and we plug that into some other function, h of x, where h of x is arcsin of x. And then this little bit right here would be h of g of x. And then if we have another one, which we could say a g, h, I, j, how a k of x is tan x, then we could write this whole thing as k of h of g of x. And in general, the best way of figuring out this type of thing, in other words, when we're trying to figure out the domain of something, it may seem like purely academic, like why would we care about that? If you've ever written a computer program, like pretty much any, but like especially involving mathematics, this is a kind of thing that you absolutely 100% need to figure out. Because you need to be able to tell the computer, hey, hold up, there are certain things that are not in the domain. Like 0 might not be in the domain. Don't plug it in. And tell the computer to figure that out ahead of time. But also, I mean, there's a bunch of reasons why, not just for computer programming and whatnot, but this actually comes up a lot. And so, in general, the best way of doing this, when you're trying to find the domain of this thing, right, because that's what we have now, we have that f is some function which is a composition of 3 separate functions. The best way to do it is to go all the way to the input, right, because domain deals with the inputs to a function. So we're going to start by looking at the inputs, okay? And since the innermost thing that's in here is this function right here, I suggest that we go ahead and graph that bad boy. See what it looks like, okay? So, what type of object is this? 1 minus x squared?
Perhaps the line. Wait, no. Right. Yeah.
It's a parabola, right? And it looks, is it an upward cup or a downward cup?
Down.
Downward. And I'm just going to go ahead and do it. It looks like this, right? What's this point right here? 1, right? Because you could think about it as negative x squared that's been shifted up 1 unit. And then it has zeros here at negative 1 and 1. Okay, so that's just to start off, right? This is where we have here. And the question is, are there any restrictions to that?
It can't be big. Oh, for the ring. No,
Just
for the domain.
this function by itself, just 1 minus x squared.
No.
Is there anything, I could plug any number in for x, right? X could be any input. So if we do have any restrictions on the domain, it ain't gonna come from this guy right here, right? Okay, now let's see the next thing. The next thing is arcsin of stuff, right? Arcsin x, let's say. And we could graph that and see what he looks like. Plug in an x, comes up like this, up to pi over 2. And what's the input here, the biggest input we can allow? 1. What's the smallest input we could allow?
-1.
Cannot go outside there, right? That is, if we go outside there, we have a problem. Because if I try to plug in, say, 2 into arcsin, it has no meaning. It doesn't mean anything. It means you plug something into sine and got out a 2. What did you plug it? Well, you didn't plug in anything to get a 2. That's just not true. So what we're going to have to do is this. Like this is going to be my first step here. I'm going to say, well, since I could only plug in stuff from -1 up to 1 into here, and the inputs to this guy are the outputs of this guy, what I need to do is find out this part right here. Okay? So, in other words, what inputs can I plug into this that will give me, that are allowed, right? And clearly, everything from -1 to 1 is going to give me stuff all the way up to 1, nothing bigger, so we're good there. That's going to take care of that part. But what about down to here? Can I find these points here? What input here, let's do the positive one first. What input here gives me -1 as an output?
Sorry, see this guy.
Wait. In other words, you're trying to do this, right? We're plugging in some number into here. Out pops a -1. So how about let's bring the x over here, the x squared. Add that guy over here. We have 1 plus 1.
Square root.
And check this out. When we take a square root, we get a plus and a minus, right? And hey, look at that. We can see that, yeah, there should be 2 places where the output is -1. Here at plus root 2, and here at negative root 2. Right? So let's just kind of follow this logic through, okay? If I plug in a negative root 2, I get out a -1, right? And let's just check that, right? 1 minus negative root 2 squared is the same as 1 minus, well, negative root 2 squared is a positive root 2 squared, which comes out to just be a 2. 1 minus 2 is -1. Then if I take that, can I plug that into arcsin?
Yeah.
Perfectly fine to do. You have no problems doing that. You'll get out a negative, you'll plug in your -1 and get out your negative pi over 2. You're good to go. Ditto all the way up here. Start plugging in values in between here, this entire interval here. So it looks like we could include root 2. And as I move all the way up to 0, I'm just getting numbers that come all the way up to 1. No problem there. I could plug all of those into there, and there's a perfectly well-defined output. Continue on, and well, I guess you go back through the same ones, right? You get all the ones from 1 back down to 0, so you're coming all the way back down and getting those, no problems there. Keep plugging stuff in all the way up to positive root 2, and what happens? Well, you go from 0 all the way down to -1, so your inputs go from 0 down to -1. Perfectly good, right? No problems yet. Does everybody buy that? And just to see what I'm talking about, right? If I plug in a square root of 2 into this part right here, right, I would have arcsin of this stuff, which would give me arcsin of this stuff, which is arcsin of this, which is perfectly good. I could plug it in and I could get out a thing. And so it looks like, as of right now, all of these bits are in the domain. So my candidate thus far is that my domain, it looks like, I'll do it over here. It looks like my domain is shaping up to be something like -√2 all the way up to √2. But we're not done. Because tangent has problems at certain places. We can't just plug in anything we want into tangent. And so what I'm going to do is say, well, one thing we notice is that the outputs of this are going to become the inputs to that, right? And so if the outputs go from minus pi over 2 all the way up to pi over 2, I don't need to go all the way out to like 10 pi on both sides. I'm just going to look at what happens with tangent. I know he looks like this. He shoots up and has an asymptote here at what value? Pi over 2. He comes down and has an asymptote here at what value? Negative pi over 2. Now, as it stands right now, notice where my problem's going to be. If I plug in a -1, right? And this is kind of, now I'm just kind of tracing my way backwards. And I'm remembering that if I plug in every single one of these, right? If I include these endpoints, what's going to happen? Well, if I plug in a minus root 2 into here, it squares it, comes out to be a -1. So that part's -1. So then I plug a -1 into arcsin, and out pops a -π/2. So now this entire thing has become -π/2. Can I plug that into tan? No. Bad news if you try. So we're going to have to remove the point that gave me that negative, that bit right there. And so I'm going to say, well, what was the input that gave me that? Well, it was this guy right here. We have to remove whatever gave you that -1. So I'm going to come back here and say, well, what values here gave me a -1? Well, there's two input values that gave me a -1. One was minus root 2. The other one was positive root 2. So I'm going to need to remove both of them. Okay? Now, does that make sense? Right? Because if I go all the way out to root 2, right, I'm thinking about this. Can I plug in root 2? If I plug in root 2, it gets squared, right? Take 1 minus it, and you get a -1. Plug in a -1 now into arcsin, and you get out a -π/2. This whole thing is -π/2. Tan of -π/2 is bad news. We have to remove it. That's why we removed both that one and that one. Are we done? Hold it right. Where's the other part of tan that could cause problems? I mean, we did this one.
Oh.
How about this one?
Pulling that itself back on.
What's that?
We already did that. Yeah.
We did -π/2.
We put us.
We did -π/2. We said -π/2 would be the output of this guy. This came from, well, both of those.
Oh.
But we have another problem, don't we?
pi/2.
Pi/2. And so if pi/2 is going in, where did that come from here?
Positive.
It must have come from the +1 right there. The +1 must have come from 0. And so we're going to have to remove the 0 as well. And this is what we should have. This is why I said this one was hard. Like I said in the email, I was like, this one's hard. And so finally, we end up with this right here. That guy. That is the domain of F. Yeah, quite hard, but it's kind of easy once you see this, right? Like, in each step, you're just kind of seeing, well, what can't I plug in? There's no problems here with plugging stuff in. There's problems outside of here. So how do I restrict it so that this is that interval? Again, I can't go past here, so how do I restrict it so this is that interval? Well, there's no problems. Oh, there's problems on the endpoints. Get rid of the endpoints. How do I get rid of the endpoints? Well, I get rid of these endpoints. So I get rid of those endpoints, right? And it's kind of, you know, there's a visual way of doing it. I think it makes a lot of sense that way. I'll do the other way of doing it, which it may not always work. It'll work in this case, but as you'll see, it's a little bit more complicated. But since we have the domain there, let's figure out the range. So let's just think about this. Now that we know what the original inputs are, we could just kind of trace this through and say, well, if I plugged in everything from here, I would get everything except for -1 all the way up to everything except for 1. So in a sense, what I'm getting is this. I'm putting holes here, right? Have you guys seen that before? Yeah. I don't think we've done that in our classes, but that's usually how you do it. If you're going all the way down there, you don't quite get to -1. And so that interval would be then this interval, the open interval from there to there, which would be this interval from here to here. So we're not getting the endpoints, but we'll get everything except for those endpoints. So we'll go all the way up to there, but not quite getting there, all the way down to there, not quite getting it. And hey, lo and behold, what are you going to get? All of that stuff will go in, and we should get all real numbers.
What does it look like?
So you'll notice as you go from here to here, you're going, as you go from negative root 2 up to 0, you're putting in these numbers backwards, right? You're getting, you plug in -1 and you'll start here and then you'll move up to 0. So it should look like, oh, all the way up to 1. So you're starting here and moving all the way up to there. So you're already going across this one full unit. So so we should start low and end up going high like that. Can't plug in this guy, so we're going to skip over it. Now we're running backwards. We're starting here at 1, which gives you that, which gives you that. So we start up here and move our way back down like that. It should look something like that. Though I didn't ask you to do that, but like that would be. But you notice you are getting this entire interval twice. You're going from -1 to 1 as you go across there, and then you're getting from 1 back down to -1 again. So it traces this once, traces it back, which means you go there once and there back in the time that you run from here to here. And you should asymptotes there, asymptote there, asymptote there. Yeah. Yeah, that was a hard one. That was a very hard one. But I gave you each a point because you tried, which is good. Now there's another way of doing this. There is another way of doing this. And right off the bat, you could say, well, hold up, I have an arcsin. So why don't I do this trick? I'm going to let some angle theta be arcsin of my stuff. Right there, you could say, well, if that's the case, I could set something up like this. And if theta equals arcsin of something, then sine of theta is the thing, right? And so I could say, well, sine is that over that. And so I could just make this 1 minus x squared and make that 1. Now here's where you're going to mess up. Here's where you messed up. Where, and I said this before, right? You might just say, oh, that's the square root of that one and that one, right? Well, hold up, because it's this squared plus this squared equals that squared. So it's 1 minus x squared squared plus b squared is equal to 1 squared. So then b squared is 1 minus that stuff squared.
So that's square.
Then you take a square root and you take the positive square root. And so we have this. Oops.
This was later. Wait.
You had a plus out here. Like I said, it's always going to benefit you to just go ahead and write out the Pythagorean theorem, because you're inevitably going to mess it up if you don't. Because if you say, oh, yeah, the Pythagorean thing, it's that one plus that one squared, and then you take a square root. Well, yeah, if that's the one you're looking for, it's plus. But if it's one of these, it's going to end up being a minus. So, kind of a pain. But nonetheless, we got it. And we could say, okay, then b, this guy right here, should be the square root of 1 minus x squared squared. There you go. Okay, so now we're going to say, all right then, this right here, we could just replace this with theta. And now we have tan theta. Tan is opposite over adjacent. So this thing is just 1 minus x squared over square root of 1 minus x squared squared.
Like I also did.
And I think you did, but there was a plus there. And so, almost. Now, here's the question. Well, no problems there, right? If I just said, hey, here's your function, there's f of x. What's the domain? Well, you wouldn't care about that. You would only care about when that thing is either equal to 0 or the inside is negative, right? Like that's what you do. If I said, here's f of x equals 1 over 1 minus x, or let's say the square root of that, you would say, well, we have a problem if x is 1, because that causes 0 in the denominator, and we know that we need to make sure that this entire thing is positive. So now we have two things to deal with. And I'm going to say, and I'm going to take care of them separately here and say, okay, let's do the 0 part. This thing cannot equal 0, so let's find out where it does equal 0. So the 1 minus x squared, find out where that equals 0, and wherever it does equal 0, we have to remove that from the domain. So a few different ways we could do this, but one way I'm seeing right away is to just take this guy over to the other side. Now we'll take a square root. Square root both. Yeah. It gives you plus or minus 1 equals 1 minus x squared. Now we have a couple different ways. You bring the x over, I guess. Bring this guy over, and that'll be a minus plus 1. So now we have two possibilities. X squared is either equal to 0 or x squared is equal to 2. Take a square root of both sides, you get x equals 0. Or x is equal to plus or minus root 2, and we say we cannot have those. So we're talking all real numbers here. As far as we know, you possibly could plug in every real number, but now we found 3 that we cannot use. So we're removing 0, we're removing negative root 2, and we're removing root 2. And as far as we know, everything else is still valid. All these down here, as far as we know, are good. All these here are good. All these here are good. All these here are good possible inputs. Okay? But there's one more restriction. This thing now has to be bigger than 0. Okay? So this has to be bigger than 0. And again, you could multiply all this out, and you'd have a 4th degree polynomial. Then you'd have to use quadratic formula and all that. But then again, we're not talking about solving for 0. We already did that. Here we're talking about, you'd have some kind of 4th degree polynomial, doing something like this, and we'd have to find out, where is it bigger than 0? Well, we should have a couple intervals on which that's the case. Good luck, you know. But in this, and you see what I mean, like in general, this actually turned out, this in particular, this problem turned out to be something that we can analyze this way. But in general, it might not look this good, right? We got lucky that it looked this good. So I suggest to do the, just draw the pictures, see, okay, well this turns into that, which turns into this, which turns into that, which turns into this, which gives you that. We have problems here, pull these out, which means we have to pull those out, which means we have to pull these out, which means we have to pull those out, which means we need to pull these out. It's easier. In this case, your work is about the same, but we got lucky because this is actually doable. And I could say, okay, so now we're looking for when is 1 less than this, 1 minus x squared. Squared, now what happens when you take a square root with an inequality?
Nothing. Wait, it flips it? No, it doesn't. Oh, it's like that.
It's like the absolute value, right? It's that we take a square root of both sides, but what that means is then the absolute value of this thing has to be
plus or minus.
less than, but you see that's where the plus or minus doesn't really work. Or does it? You see, and this is what I mean. Like, is it also plus or minus or no? Because you're talking about absolute value. Of course the absolute value is going to be bigger than a negative number. So
the minus 1 doesn't really.
You see what I mean about this is like we have to deal with all these like nitpicky algebraic things. And so we could continue on here and say, well, what this means is that this has to be bounded above and below here. Which means, okay, so I'm going to subtract off a 1 from each side and get a 0, negative x squared minus 2, negative, I'm going to multiply through by negative 1.
And that flips it.
That flips it. And so x squared, okay, again, now we have x squared, of course, bigger than 0, but here, too, so I'm going to have to take a square root But when I do that, that means that the absolute value of this thing has to be bounded by this, which means again, then this is there. And now we finally got the same answer we got. But I guarantee you, if I were doing this, I would mess this up somewhere.
Yeah.
You know what I mean?
I didn't even get this far.
Yeah, exactly, right? And so we see, okay, it has to be between these. And so finally, the intervals that we can have are these in here, all these in here. And so our final interval would be from here to here, here to here, union those together, and we get the same thing that we got before. Another way of doing it is to say, well, check this out. 1 minus something has to be positive, so that whatever goes in there at biggest can be 1, okay? And then you just kind of go through and say, well, if it's squared, we don't really need to worry about that. If it's 0, it's fine. It works all the way up to 1 and so on and so forth, but you're still kind of, you're messing with symbols, you know? I'd much rather mess with pictures in this case, because I guarantee you I will mess up these rules. And I'll put them on the wrong side or something. I'll be like, wait, is this the one that needs to be on either side of that? And so, very hard problem. But it was an extra credit, so it didn't hurt you. So, okay, are we ready to move on?
Yeah.
Okay. And of course, range, same thing as before, but now you don't have pictures to help you. So now you'd probably, if you had gone this route and found the actual interval, you'd now be like, okay, now let me start plugging things. Can I graph this? What's going to happen? But if you've already drawn your pictures, you're good to go. So we're moving into chapter 7. And chapter 7 begins with my favorite thing. Identities. So we're going to do identities. All of these are just verifying identities. And really, I've given you the best that I could give you as far as identities are concerned. You know, I told you, when in doubt, change everything into sines and cosines. Start with the more complicated side. These tips aren't I don't have any new tips and tricks for you, really. And the way to do these is to just do them, okay? One thing I am going to say, though, you're definitely going to get stuck. Did I give you 33? 33. You're just going to look at 33 and go, what? And maybe you'll say, well, let me start on this side with the tangents, and I'll turn the tangents into sines and cosines. That's a good one. But you're going to get stuck a few times here. And what I'd suggest is if you're completely stuck and you've tried the tricks that I've talked about and everything, and nothing's coming forth, the answers are back here. Except for these last two. The answers are back here, and what I would suggest that you do is you look at the answer, you cover it up, and just look at the first step they take. Because each one of these are like proofs, right? I did like identities. It's step by step by step. Change this side of the equation into this side of the equation. And I would say, just, because why do we do homework? It's not to turn in homework. It's so that you learn how to do this, right? So I would suggest that you start off looking at, just look at the first line. Cover everything else up. Look at the first line, and then maybe you go, ooh, 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 I never would have thought of that. And there's a couple of those in there I was looking at last night where I'm like, ooh, I never would have thought of that. That's a good one. And so you could learn from that, right? And that's the whole point of this, is that you learn from this stuff. So I would start with that. Just cover one up, and then try to go until you get stuck. Maybe look at the next one, and so on and so forth. But don't look at the whole thing. You'll kind of give it away. You know? So there's a couple of these I did want to do. 34 is just terrible. Let's do 34. This is number 34. Tangent U minus tangent V.
Two? Is that just like... those are just random unknowns?
Those are, what, say again?
Are they just variables?
Just variables. Yep, everything in here is just a variable. You might have a 3 beta. There's 2 theta. U and V, alpha, X. These are just variables. tan u tan v over 1 plus tan u tan v is equal to cotan v minus cotan u should have got this. Cotan u, cotan v. I can't prepare for this. Watch what we're about to do. Give me just a second. So like I said, like we're going to do a couple examples, and there's hey, hi buddy, and I really can't give you much more than just working out a couple examples with these. Because you just have to get your fingers dirty. Like, you gotta get your hands dirty and just do it. So, we'll do a couple examples. We'll see how well this works. But then there are other things in this homework that are, that I do want to talk about, and it will be good for us to actually go over. So, let's see. Can I do this? I better do it this way. Hey, bud. How you feeling, boo-boo?
I thought you couldn't like subtract or multiply or something when they had different inputs.
Wait, say again?
Like I thought since tan U and tan V have different inputs, you can't.
Well, yeah, and that's part of the problem, right? So, like, for instance, if it were on the top tan U minus tan U, it clearly would be 0, right? So this is,
Okay.
yeah, we are talking about two different, let's put you this way. Oh no. Oh no. Well, hopefully we don't get really messy here. I'm sorry, buddy. We'll just do this. That's probably why you woke up crying, huh? All right. Okay. Say hi to the guys. Okay. Oh, come on. Where is it? Oh, it's under my hand. All right. See how well this goes. Wish me luck, everybody. All right. Okay. So, yeah. So you noticed, right? We can't just combine them. These are different things. Because U is not V. Right? Unless it is, in which case, yeah, it reduces down to 0 equals 0. But we don't know that. So what I'm going to do is this. I noticed that we could rewrite cotan in terms of tan. So maybe that's where I'm going to start. You know, I don't know. Maybe there's some kind of, another thing you're totally going to want to remember through all of this is cosine squared plus sine squared equals 1. From that, you could divide everybody through by cosine, and you get tan squared equals secant squared. Divide everybody through by sine, and you get cotan squared 1 cosecant squared. You're going to want to use these when, you know, you're probably going to have to use these a bunch. But notice we don't have a tan and a cotan, so that's not going to help me. So I'm thinking I'm going to take this one and turn it into just tangents. And that's where I'm going to start. So I'm going to say 1 over tan V minus 1 over tan U all over 1 over tan U times 1 over tan V minus 1. Geez, I don't know. When you see something like that, what does your brain scream at you? Kill denominators. Oh, that's exactly what I wanted to hear. Yes, it's kill denominators, right? And I don't know if that's going to help or not, but at least it'll make my life look easier. So if in order to kill that and that and that and that, I could do that with tan U, tan V. So I'm going to do that on the top and on the bottom. So that jumps over the v's die and the u stays put. So there's tan u. That jumps over the u's die and the v stays put. Now, tan u, tan v kills those guys. Tan u, tan v. Is that what we wanted? Yeah, that's what we were trying to prove, right? So, in your write-up, right, this, you do some scratch work and stuff like that. In your write-up, I want to see explicitly, you start with one side of the equation, so it would look something like this in your work. You start with one side of the equation, and then all you have are equal signs for every step you take until we get to the end. Okay, now notice what I didn't do. I didn't go and turn everybody into sines and cosines. I could have. I could have started by saying, let me just turn everybody into sines and cosines. But I noticed that tangent and cotangent had this nifty relationship, so I didn't need to go that far into it. But if I had like a cotan and a secant or something like that, yeah, I'd probably turn everybody into just pure sines and cosines to go off right there.
Wasn't the left-hand side 1 plus tan? Or did I misread it?
I think I might have miswrote it. Oh, it was. What did I do wrong? 1 plus. Oh,
Well,
no.
it should be 1.
Wait,
Oh, wait.
it was. Thank you. What did I do wrong? They both should have been plus on the bottom. That's where I messed up. They both should have been plus on the bottom.
Oh.
And so that would have been plus, and that would have been plus,
Yeah.
and the other finally would have been plus. So I just copied one of them down wrong. So good catch. Excellent catch. Okay, so that kind of stuff. Let's do another one. Did I give you? I did give you that one. So let's do. So another thing you're going to want to get really familiar with these is these. If you have sine of negative theta, that's the same thing as what in terms of just plain old sine theta?
Negative sine theta.
Negative sine theta. Now what about cosine negative theta?
Just cosine theta. Right?
Yes. You messed that up on the quiz. Yes, right? Because this is an even function, right? Right? Cosine looks like this. And so if you're over here at theta, you get whatever output this is. But if you're down here at negative theta, it's the same output, right? It's the same. Whereas sine, it's the negative of the output. So whereas sine did that, now you're down here at negative theta, it does that right there. Right? It makes that value negative. So you're going to use that a lot. That also means that tangent, what about tangent? Tangent negative x equals what? In terms of,
Wait.
yeah,
Yeah, negative.
negative tan x, and so on and so forth. You're going to want to use those liberally. They're going to pop up a bunch. I did want to do one of these. So, number 50. I can't believe you pooped again, dude. How many times are you going to poop today? And I hope this isn't getting all over us right now. So, let's do this. Ugh. Okay. Actually, let's use this. Looks good. The natural log of.
It got over.
The natural log of. Now, I'm going to use parentheses. Your book does not. And so just know that this is what it's doing. Cosecant x minus cotan x.
Wait,
Absolute value of that.
Oh,
The absolute value. Because you can't put negative things into log,
Yeah.
right? Cosecant takes on positive and negative values, so does cotangent. And so you gotta restrict that stuff. That's what they're doing there. Show that that's equal to negative log of the absolute value of cosecant x plus cotan.
Well, we can relate cosecant to cotan.
We can.
But, oh wait, there's
So when I see a negative in front of a log, I don't know about you.
oh, you can just flip the thing in.
Yeah. So my intuition is to start on the right hand side here. Now let me make sure I wrote this down right this time. Log cosecant minus cotan. Log cosecant plus cotan. Yes. Okay. So my intuition is to start with the negative log. That's what I'm going to do. So I'm going to start with this side and say, well, the negative comes up like that, right? That's what it does, right? It's a negative one out front. It's our favorite property of logs, that exponents come out or go up, right? That's the nice thing. So this side of the equation is equal to this, which is the same thing as natural log of 1 over this stuff. I'm going to go ahead and tell you, don't worry too much about these absolute value bars. There might be some, no, we're not going to worry about it. I never worry about it. And I made it through a bachelor's in math without having to worry about it, so whatever, you know. He's like, usually when you have absolute value bars in log, it's just so that everybody knows we're not going to plug in positive factors. We're not trying to be tricky or anything like that. That's all it is. But now, when I'm looking at this, I'm like, well, that sure doesn't look like that. So maybe I'll just go into sines and cosines. Maybe that'll help me. And for right now, I'm going to forget about these absolute value bars, and we'll just come back and deal with them at the end. Whatever. I'm not worried about that. So what I'm going to do is go 1 over, cosecant is 1 over sine. And notice I'm dropping the x too. Cotan is cos over sine. I don't mind if you do that, but look, there's only one variable. This would not have been, I would not recommend doing this in the last problem where you had a u and a v, right? You know what I'm saying? Right? And you have 2 variables, you'll need to keep track of them. You can't take this step. But, okay, now, what do you want to do?
Well, cos over sine. Wait. Oh, cos over sine is cotan.
Mm-hmm.
Wait, but
That's what I
never
did.
mind.
Yeah. So when you see that this type of beast,
Oh, we can combine? Or
Yeah,
kill the
there's a
denominators.
common denominator.
Multiply it by
okay, common denominator. Okay, so then we have what?
1 plus cosine.
1 plus cosine over sine. So this is natural log of 1 over 1 plus cosine over
Then we
sine.
can get rid of, I kill the denominator.
Yeah.
Multiply the top and bottom by
Or we could flip it. and
Or you could
multiply
flip it, right? And another way to do it would be to multiply the top and the bottom by sine here, and we'd end up at the same place. Natural log of sine over 1 plus cosine. Now at this point you're going to say, this looks nothing like where I'm trying to go. So maybe what we're going to do is say, well, let's play with this. And maybe I could turn this. So now instead of trying to turn this thing entirely into this thing, maybe we could turn this thing into this thing. And then come back, turn this thing into this thing, and now we'll have a good roadmap for how to get from point A to point B. So that's what I'm going to do here. I'm going to say, so this, the left-hand side, is equal to natural log of, forgetting absolute value for now, that's 1 over sine minus cosine over sine. Yeah?
Oh, wait, no.
No? Yes.
Well, yes, but 1 minus cosine.
And so this is natural log of 1 minus cosine over sine. Now what?
Oh.
We'll work.
We're close. We're real close.
Oh, you can take out the negative, and then, because it flips it. Oh wait, no.
Yeah, I like that, right? Like you could take out the negative.
Like say it's to the negative, like flip it and say it's to the negative. So like natural log of 1 minus cosine over sine is the same as natural log of sine over 1 minus cosine to the negative 1. Does that make sense?
So you're saying we go log cosine minus 1 over sine, but it's negative.
Wait. No.
Oh,
So
just saying flip it and make it negative.
flip it and then have it like raised to negative 1.
Yeah.
Because then you can, does that make sense?
Absolutely. We say sine over 1 minus cosine to the negative 1, like that.
Yeah.
That's what you're saying. Yep.
And then,
Then what? Pull out the negative 1.
but, oh,
What if we just set them equal to each other?
Where?
we can just set them equal because
Step
then and try to
before.
solve it.
Do what? Where? Which ones? I mean, I'm
The
wondering.
step right before the exponentiation. The negative one.
Set log n of sine over 1 plus cosine equal to the log n of 1 minus cosine over sine. And then try to like solve
Then
it,
you could
but you can't.
divide by natural. Wait, no, that's not a good idea.
So let's see. Let's see where we've gotten to now. So let's make sure. So now I'm glad that we're hitting walls because this is what's going to happen in your homework, right? Like left-hand side. Let's make sure we copied everything right. Cosecant minus cotangent. Cosecant minus cotangent. Okay, is 1 over sine minus cosine over sine. Did I do that right? Yeah. Which is equal to that. Okay. Negative of that stuff. Maybe, I don't know, like we ended up here. Maybe let's leave that negative out for now. I don't know. Like, you see what I'm saying? Like, I'm not exactly sure. Not exactly sure. But let's try this now. So right-hand side.
Oh, I see.
So right-hand side is going to be negative log. Now, I'm forgetting about absolute value for now, but this is 1 over sine plus cosine over sine, which is the same thing as negative natural log of 1 plus cosine over sine.
Yeah. And then,
Are we any closer? We're still there. We bring it up and flip it. So it comes down to somehow we're going to have to, if we could show that, and let's go ahead and do this. Log of that. So notice what I'm doing. I'm bringing the negative up into it. I'm just going to go ahead and flip it, just to save space. Everybody got that? That step I just took?
yeah.
Brought the negative 1 up into the exponent. Negative 1 just flips the stuff. So now, is there a way that we could show that this is equal to that? Because as of right now, we have log of this stuff equals log of this stuff.
Oh.
Maybe? So let's just see. 1 minus cosine over sine. Is that equal to sine over 1 plus cosine?
So kill the denominators.
So let's cross multiply, right? I'm going to bring the sine upstairs. Bring
Oh, and then
this upstairs, 1 minus cosine, 1 plus cosine. First outer inner last. 1 outer inner cancel minus cosine squared
Oh.
is sine
Oh,
squared.
there we
go.
Oh, it's so hard. so hard. And so, but here's the question, can we reverse these steps? Because what we're about to see is just because we could show that this does give me 1 equals cosine squared plus sine squared, which we know is true, can we take all of those steps in reverse? And it turns out, yes, we can. Okay? So I would start here, bring that over, do this, then we could divide and get that. Since that's the case, if I were writing this up, I would start there. Like now that I've done all of this work, I would start with this and say, watch, this is true, therefore this is true, therefore this is true, therefore this is true. And I would do a little star or something like that. Then what I'm going to do is write left-hand side equals this, and then I'd say by star, or like the next thing I would do would say, I would write, well, hold up, this is the same as that, therefore this is equal to log of sine over 1 plus cosine. And what I do is, with this step, I would like put my star right here. So I know what you're doing. Like this, why is that true? Because of the work that we showed earlier, right? Or you could stop and show that work, whatever, however you want to do it, right? But the idea is we're starting with the left-hand side. We're doing some work. We're showing that this is true, and now we'll just go back, right? And say, okay, well, that's the same thing as negative log of 1 plus cos over sine. You stop kicking my board. Which is the same as negative log of 1 over sine plus cos over sine, which is the same as negative log cosecant plus cotan, which is what we wanted to show. Oh. Yeah, these are tough. But most of them you have answers, and when you get, if and when you get stuck, you can look and see that. Also, the section for 7.1 is a good one. Like you should read it. It will help you. Now, 51. Did I assign 51? I did. We're just going to do 51. Can I get rid of this stuff? Any questions on this? Okay, so I have been so adamant about, well, one, whenever you're doing one of these, turn one side into the other in one logical stream of consciousness, right? Now, I've also been adamant about, you could go one way. If you go and show something the way that we just did and we ended up with something true, that you must show that going in the opposite direction is true. This is a prime example of why you want to do that. For 51 through 59, it says, show that the equation is not an identity. 51 is this.
So,
Disprove it. And it suggests that you find one value that shows that it's not true. Yes, that's what I thought it said. Okay. Show that this is not cosine t equals square root of 1 minus sine squared t.
Oh wait, no,
Now-
squared. Wait, no.
No, because look at this. Watch what happens. You, doing the things that you do, would say, well, wait a second, I could prove that this is true. I'm going to square both sides. And so you square both sides,
Oh.
and you go, okay, I've squared both sides. Now I'm going to bring him over.
It works.
It works, but it doesn't work. Because let's go in the opposite direction. So while this is true, does it work in the opposite direction? Let's start. Starting here, I'm going to say, okay, then cosine squared t is equal to 1 minus sine squared t. Yeah. Now what do I need to do? Square root of both sides. What happens when I take a square root of both sides?
Plus or minus.
Oh. So it's not exactly always true for every value, is it? And this is the problem. Is that, yeah, it will be true just as long as you're taking the positive ones. Tell me a value So where is cosine negative? Let's think about cosine being negative.
Oh, yeah.
Let's think about this. So it comes through at pi over 2. Let's do one. How about one that's easy? How about pi over 3 gives you 1/2, right? So cosine pi over 3 gives you 1/2. So then in that quadrant, how about 2 pi over 3? So cosine of 2 pi over 3 is negative 1/2. So let's plug in into this original thing here, 2 pi over 3. So cosine 2 pi over 3 equals, as you claim, is equal to sine squared 2 pi over 3.
But I thought we proved this a while ago, that cosine.
Only when you're in the first quadrant. As long as you're in the first quadrant, it's perfectly good. When you step outside that first quadrant, then you get stuff like this.
Yeah.
1 minus. Now sine squared is sine squared. Sine of 2 pi over 3 would be root 3 over 2, but negative root 3 over, no, positive. Positive root 3 over 2. Which is the square root of 1 minus 3 over 4.
Which is fine. Wait, 1 minus 3 over 4 is 1/4.
1/4. Square root of 1/4 is?
1/16.
No,
Wait, no.
the other
1/2.
1/2.
Oh. Okay.
But cosine of that is negative 1/2. Oh, yeah. So that would just prove it right there. And it comes from this problem right here. Is that, yeah, as long as all the values you're talking about for cosine are positive, then this will work. It'll work just fine. But when you take a negative value for cosine, you've just lobbed off half of your answers right there.
So
right?
we can just plug in a number that we know it doesn't work, and then.
And you've disproved it. But you see what I mean about being able to go in both directions? You could prove this. You could say, this is always true, always, because watch what I can do. And then you square both sides and you bring it over and you say, because cosine squared plus sine squared equals 1. This must be true. No, because you didn't go in the opposite direction. Now, it will be true that it's either plus or minus of this, but it's not always going to work with plus. So, careful with that. Okay, so that's 51 through 59. And then the last ones. These are my favorite. It is. Either show that the equation is an identity, or show that the equation is not an identity. So we don't know. Up until this point, you've been told, this is true, prove it. Or, this is not true, find a counterexample. Now, it's you figure out whether it's true or not. And so, let's do one that's actually in the answers in your book. Because I gave you the 2 where the answer is not in your book. So let's do, it's cosine x tan. So have I made my point about just because you could go from one thing to another doesn't mean that you've proven anything? Like, is it you know what I mean? Like, I've been stressing this for a couple of years now. And it's, that's why it's so important. Because you think, well, yeah, look, square both sides, you're good to go. But it doesn't always work. Plus cotan x. Equals cosecant x. So, one of these sides is the one I want to start on. I want to start on the left-hand side. And one thing I notice is the right-hand side, I could rewrite that in terms of sines. And I'm just thinking it's probably going to be easier if I just initially start with the left-hand side and write everything in terms of sines and cosines. So this is sine over cosine plus cotan is cosine over sine. Now let's go multiply through. That
Oh.
kills that.
Yeah.
That gives me plus cosine squared over sine. Okay, maybe if I get a common denominator, I don't know. But if I stop right here and say, well, that's not that, so it's not true. I might be wrong. I don't know. Like, I'm thinking, okay, this, the right-hand side, is the same thing as 1 over sine. I have something over sine, so maybe if I get everything over sine, I'll be good to go. Maybe I'll see something. So in order to do that, I need, okay, so I have cosine squared over sine. I have a sine in the numerator. I need a sine in the denominator, so I'm going to multiply top and bottom by sine. That makes that guy sine squared. And I have over sine, cosine squared plus sine squared is 1. 1 over sine squared is that. Nice. Hey, that's kind of cool. So, yeah, it's true. 1 over sine. And so, finally, right, I'm not done here. I'm going to go, that's the same as cosecant. And so, now I'm going to conclude, yes, I'm sorry, I didn't put the number up here. Number 63. Say, I started with the left-hand side, ended up with the right-hand side, and so I'm going to say yes. It is an identity.